All right, well, good morning and welcome to our first presentation of the day, Why Use an Ontology. Before I begin, I'm going to briefly introduce myself. My name is Lowell Visner, and I'm the Chief Technology Officer for Securboration, and I've been with the company since 2014. My background in ontology is, briefly, I have a PhD in philosophy from the University at Buffalo, where I emphasis on formal ontology and mathematical logic. After I completed my PhD, I went to the National Institutes of Health, where I had a postdoctoral fellowship. Basically, we were applying ontology design principles to improve medical terminologies, such as the Unified Medical Language System and other medical terminologies. And since then, I've been pretty much, working exclusively in industry, and I won't run through all the different companies I've worked for prior to this, but I've been working on, applied ontology for Account Graduate School over 20 years. So that's me. Okay, so briefly, I'll go over the sort of contents of the first talk. The objective of this presentation will be to provide you with, reasons for why you should use an ontology to represent your data. Now, this presentation will by no means be exhaustive, in terms of discussing all the benefits that an ontology might have for you. We're limited to time, and I want to keep this fairly basic initially. One of the primary motivations for using ontology is that common forms of data representation, like databases or entity relationship models, are very limited in what they can say about the data. And this will be a theme for today, is that database models are, not an expressive form representing your data. So we'll begin with a summary of some of those limitations, followed by a short overview of the benefits of using an ontology to more fully express the meaning that remains implicit in our conventional data structures. For example, things we want to do is improve understanding of our data, and as a consequence, also, make it more reusable to, more than just one application. And finally, we'll end with an overview of some of the applications that benefit from the use of ontologies. And again, I'm going to stress we're not covering everything. We're just going to focus on a few examples, and happy in the future to go in depth with other benefits, other applications that ontologies benefit. So why focus on databases? And here we're talking, primarily about relational databases, but a lot of what we're going to say would also apply to NoSQL databases, like that, using JSON or XML or various other kinds of databases. But again, we'll focus on relational here, which is by far probably the most common way organizations store and represent their data. So it's good to understand the limitations of representing meaning in these types of databases. And we can kind of frame this problem if we go back, to the history of computer science. And I think we can kind of point out, sort of use this as a framework for this, identifying the semantic limitations of databases. So Nicholas Wirth wrote a book back in 1974 titled Algorithms plus Data Structures Equal Programs. And basically what he was arguing here was that programs consist of two components: the algorithms, which is the code that processes data, and the data structures, which are the declarative structures that we use to organize our data. So the meaning that gets represented within a program is going to reside in one or two of these components, if not both. They're going to reside in both, but it's more of a balance. Is most of the meaning represented in the data structures, or is most of the meaning represented in the algorithms or application logic? The more meaning we put into the program's data structures, the less work an algorithm has to do to exploit that meaning. So, basically what we're saying here is it's better if we can put more meaning into our data structures. But if we don't have the right sort of way of representing data, it's going to be very difficult to do. And databases and other forms of structured data are severely limited in the kind of meaning they can express within their restrictive data models. So as a consequence, the program's semantic content often gets mostly expressed in the application logic. Now, one thing I just want to make clear, we're not saying that all of the meaning that's necessary to have a program or application work is in fact stored in the program itself. I mean, we know for a fact that a lot of that information is stored in the heads of data SMEs and software developers. But insofar as the meaning does get encoded into a program, the more we can put into the data structures, the more understandable it will be to people, the simpler the algorithms will be, and the more reusable that data will be for other applications existing or future. So how does data get represented in databases? So conventional databases focus primarily on a few important kinds of entities in the domain. So when I say that, I mean, people, organizations, products, and the attributes they have, like birth dates, names, that sort of thing, the types of values each attribute may have, and a few hardwired relationships among entities as defined by inflexible relation tables and foreign keys. That's another kind of data model that's it's useful in building this are entity relationship models, if you've worked with those as well. Now, this makes data storage and retrieval effective and efficient, but it has the side effect of squeezing a lot of the meaning out of the data. If the meaning's not represented within the data structures, it must be expressed, again, within typically complex algorithms or require data SMEs to interpret. And some of the examples we're using are going to be simple examples, but if you've ever worked with a real application database, you know that the data you're interested in understanding is often spread across multiple tables, and how that data is put together into a meaningful information is something that's opaque to you, to say the least. As a result, the meaning is inaccessible to other people and applications. So one answer to the question, why use an ontology, is ontologies put the meaning back into the program's data structures, where it's easier for both humans and applications to understand, access, reuse, and extend. Another thing we might want to stress here is, when we're talking about a single application, the data is meant to serve that application. But if the data in your organization is something that would need to serve different applications, then taking what you might call a data-centric view of your data is probably advised. And again, ontologies are going to be very helpful in that area. Another feature where ontologies are useful is they include axioms and rules. So this means you can apply these rules to your data, allowing you to grow the amount of data or knowledge by asserting new kinds of facts in your database. So then let's just walk through an example of what we're talking about. We can call this tabular semantics because it's the semantics of tables, which is basically what you're getting when you're dealing in database models. So in this example, the database table represents people. So we have two examples here, Jack Gunchi and Jill Gunchi. Those are individual people. Each person is a record in this table. Each column represents what we call an attribute. So city, somebody, the location information. And then the values are the cells, like Melbourne. So we know Jill Gunchi, lives in, we assume that, right? That's implicit, that Jill Gunchi lives in Melbourne, Florida. There's also things like foreign key values, which are relationships to other tables, which have information about those entities. And one thing you kind of want to point out about these database structures is not only we're kind of showing it's implicit. We assume that Melbourne, Florida is the address of Jill Gunchi, but sometimes we actually we overload these structures with more meaning. So here we have a case of referential ambiguity, right? If you read that, all those attributes in that table or columns are attributes of a person, except the last one, last updated. That's not something, I don't think people are updated unless they're, AI bots or something, they might be updated. So that's, a lot of times we're talking here about two different entities, the record and the person the record refers to. So In this example, it's important to note that relationships are based on shared values among records in different tables, rather than what we might call semantically rich relationships that can be exploited by applications and understood by people. The result is that even if records are connected by foreign key values, the resulting graph is not very meaningful and is in fact very sparse. Finally, databases have no rules of inference or axioms. So you can't really reason about domain entities and data and create new data from existing data. To increase the meaning of a program's data structure, we need an ontology, which is a data representation designed to make the meaning more explicit in domain data. More specifically, an ontology adds considerably to the kinds of semantic relationships that obtain among objects in the knowledge base, providing a kind of semantic glue that combines concepts into more robust knowledge graph. All right. So data representation benefits of an ontology. And this is, what we've been talking about is how can ontology shed light on the domain meaning missing in your data? So in this section, we'll summarize some of the benefits of ontology from a data representation perspective. How can an ontology improve the representation of meaning over other data representation techniques like databases? In short, with an ontology, more meaning can be expressed in the ontology's data structures and less so on algorithms to produce meaning. Okay, so here, we need to give ourselves a working definition of what an ontology is. The purpose of this presentation is not to define in great detail what an ontology is. That will be the next presentation. But since we were mentioning the word, we probably want to at least characterize what it is. A rough definition here might be something like an ontology is a human/machine readable representation of the types of entities and relations in a given domain. I focus here on human and machine readable because it's one thing that information be expressed such that humans can understand it, but it has to be expressed also in some sort of formal representation language so that we can feed it to a machine who can take that information and do something with it. So that's why the machine readable component is important here. On the right is just a little snapshot of a formal ontology called basic formal ontology. And this is a typical fact about ontologies, that they tend to be hierarchical in nature. So you have a taxonomy with the top concept continuant being the most general thing, and something like disposition being the most specific concept in the ontology. Once you have this taxonomy, then we also like to have relations that we can define between these classes as well. Okay, so ontology benefits. So the first thing to note about ontologies is that they are what we might call reality-centered. They represent the meaning in data as real-world objects and relationships that correspond to the way people think about their domains of interest. Most databases are what we might call application-centered. The focus is on how to build data structures that primarily fit the needs of the application. So we're more concerned about what the application is going to do than we are about how the data is represented. And that's fine, again, if you are only caring about, if your view is only one application. But if you're in an organization or enterprise where that data is important to multiple stakeholders, then the application-centric view is going to have many shortcomings because you won't be able to easily reuse that data. Now, there exist standard ontology representation languages, such as the W3C's Web Ontology Language, or OWL. That's an interesting acronym, which model this meaning in a formal machine-readable format. So there's standards-based approaches for doing this. A positive side effect is that the machine-readable model and the human-readable model are more closely aligned than is possible with conventional database records or models. A second benefit is that an ontology provides a semantic framework that can be used to integrate heterogeneous stovepipe data. Ontologies are, to use a fancy word, are kind of lingua franca among domain data sources. So the ontology can serve as a common reference model to which legacy data can be mapped and interconnected. Furthermore, ontologies provide the meaning needed to integrate structured data with unstructured data, like text and images, making semantically integrated information accessible to many different people, organizations, and applications. And that's going to be one of the main use cases we're going to talk about today, is how ontologies can help us link structured and unstructured data. Third, an ontology-based data model is more flexible than a conventional data model, meaning that it's easier to modify and evolve the ontology over time. So if you've ever worked with, relational databases, they're sort of built with their use case up front, and adding more tables, new tables, is not something that scales over time. They become very brittle, and every little change tends to break things. So ontologies are easy to add new facts and data to your data. Once database schemes and tables and so the results of that are, the configuration management and version control become very complex in database models. Now, this can also be a challenge for ontologies, but again, like I said, they're much easier to do than conventional databases. It's also much easier for people to understand the nature of those changes in an ontology. Fourth, because an ontology is meaningful to both people and applications, and because it can be used to integrate many kinds of information, it forms a solid foundation for reuse throughout the organization, since the ontology provides a kind of virtual, unified source of data, or global schema is another way to think about it. Finally, the data in an ontology can be extended by axioms and other rules of inference. In this way, new data or assertions are created from existing data. For example, if the ontology has an axiom that says, if person X hired person Y, then X knows Y, and we have some data that John hired Sally, then we can assert John knows Sally. Those are just the simple kinds of inferences that are possible. So ontologies provide a formal, explicit way to represent meaning within a domain, so that modelers and applications can focus on the meaning of their domain rather than focusing on a data model. In this example, this graphic, we have modeled some of the relationships among entities involved in a U.S. Navy piracy interdiction mission. And this is a realistic but fictional scenario that was invented by subject matter experts. In this scenario, the aircraft carrier USS Ronald Reagan is giving commands to two of its Seahawk helicopter pilots, who are observing an attack of two merchant vessels by a couple of unidentified pirate boats. This graph representation of the mission's entities and relationships makes meanings much clearer for all stakeholders. We can think here also in ways that inference could be important. One of the things we care about in situations like this is threat assessment. So the intent, the capability, and opportunity. So, if we have information about the boat or bogey one, and we have information about, its direction, its heading, its capabilities, we can use some of the inferencing capability to say this thing is a threat or not a threat, or use some of the information to try to determine the intent, things like that. So another benefit of ontologies is that it promotes domain understanding. So our team has supported many ontology development projects with participants that range from professional engineers, bank managers, military officers, and even elementary school teachers. And in each of these cases, the collaborative process of developing a domain ontology has really helped all stakeholders to better understand their domains. Whether the focus, is on something like an HVAC system or an insurance business process, or, something maybe the people on this phone call are more familiar with, weapon systems, concept of operations. This kind of collaborative shared understanding reduces a team's dependency on expensive subject matter experts or the original developer of a complex algorithm. Ontology development is a team sport. It's not something, ontologists do by themselves, and it's governed by explicit rules of engagement, and, it's a shared vocabulary or shared semantics. That's a key feature. So, ontologies make meaning explicit for both people and applications. It reduces dependency on data SMEs and, brings more of the semantics onto the data structures and out of the logic, application logic. It exposes meaning and logical relations for use and understanding, extending, and reasoning over the model. It takes business logic based on de facto meaning out of code and makes it explicit in human and machine readable structures. Application benefits of an ontology. So like I said, there are many application benefits of an ontology, but we're going to focus on just a narrow few here for illustration purposes. So one type of application that ontologies can improve is navigation and search. Unstructured data, such as text, can be indexed using terms from an ontology to find more relevant information. For example, using ontology, the search term organization, so if you type organizations into your search bar, could be expanded to include terms like companies, social clubs, military services, and so forth. Basically, the idea is that if those terms are organized in an ontology, then we can semantically expand our search terms. So if the ontology states that a sports organization is an organization and that a swimming club is a sports organization, then searching for organizations in the data will return documents that mention swim clubs, as well as other sports organizations such as tennis clubs. So it may not even mention the word organization is the point there. In a similar manner, data from many sources can be semantically integrated using an ontology as a common semantic model, as previously mentioned. For example, the ontology may represent the unique ID of a person, which is mapped to Social Security number of a student in one database and to the employee number of another employee in another, thereby semantically integrating the two into two different attributes of the same person. Now, an example of how inferencing rules or axioms can be used to draw new conclusions was discussed earlier. However, there are many kinds of inferencing applications based on different kinds of logics, most of which require some kind of ontology for full expressive capability. One of the key tenets of all customers is that they want their investment in data to pay off by making data useful to many different applications and organizations. In other words, they want reusable enterprise knowledge. Knowledge bases developed using well-defined ontology structures provide the kind of common semantics that can be reused in many ways by many applications and organizations. So let's just drill down a little bit more on semantic navigation and search. Most text search algorithms are based on a kind of string literal search technique in which the user inputs a sequence of letters or numbers and the search algorithm matches the string. So for example, say we enter water faucet to the data in our database. This approach has some downsides. For example, and you can try this out in real time if you like, if you search for water faucet on Home Depot's website, you'll get the results types of water dispensers such as water coolers and water jugs. So the algorithm has no notion of faucet as a concept, so it does not find similar concepts that we would be looking for, such as spigot. Ontology-based search, or semantic search it's sometimes called, is concept-based, not string-based, meaning that the search algorithm looks for synonyms and paraphrases for water faucet in the search, providing results that are more meaningful to people and more useful to other applications. So we can break down these components as follows. We have synonym-based retrieval. This is synonyms within ontology provide a kind of thesaurus for search algorithm, such that if you search for ship, we'll also return mentions of vessel or boat. Taxonomies within an ontology provide a way to access all specializations of a general term. So again, if you search for ship, we'll return mentions of battleships, aircraft carriers, and cargo ships if they're defined in the taxonomy. Another feature is what's called partonymies. It's a nice word. Within an ontology that provides a way to access all components of a concept. So for example, what's a good example of partonymy? Think of the human anatomy, right? Your finger is a part of your hand's a part of your arm's a part of your torso is a part of your body, right? So that sort of information can be encoded in ontology as well and be used to retrieve information. And then finally, we get to the instance level within an ontology that provides ways to relate specific individual ships to general types, such as the USS Ronald Reagan to aircraft carrier. In such cases, a search for aircraft carriers can return all named instances of these ships, including the USS Theodore Roosevelt, along with the USS Ronald Reagan. So even the instances can be used to find information about ships. So basically, in summary, since ontologies provide explicit semantic relationships that connect concepts in meaningful ways, these relationships provide the semantic connectivity that can be exploited by navigation, search, and query algorithms, as well as any other algorithms designed to process well-defined semantic relationships. Reasoning, another benefit is reasoning with rules of inference. This will be a topic for another presentation, so I won't go into it too much. But we've kind of, talked a little bit about what we call inferencing. Most semantic web applications support what we'll call deductive reasoning, which is, given premises, it will infer new premises. But there are other kinds of reasoning that we can do as well. Sometimes these are called inductive reasoning or abductive reasoning. In deductive reasoning, a conclusion is, if the premises are true, then the conclusion is necessarily going to be true. In inductive reasoning, they give us good evidence for believing that the conclusion is true. And there's lots of good stuff on, the differences between monotonic reasoning systems and non-monotonic reasoning systems. But I'll just give you one example of a sort of non-monotonic reasoning system, and that has to do with defeasible rules. These are rules that can be defeated by contrary evidence. So if you take an example of such a rule, like birds typically can fly, and then we have some data that says Chilly Willy is a bird, so we're going to make the inference that Chilly Willy can fly. But if, at some later date, new knowledge comes into the system and we discover that Chilly Willy is a penguin, then we're going to want to revise our inference, because penguins can't fly, and therefore Chilly Willy can't fly. Yeah, it's a whole other subfield of different types of reasoning systems, and it's beyond the scope of this talk, so I'll leave it at that. But the reasoning, well, let me mention one other thing. I mean, probabilistic reasoning is another type of reasoning that can be supported by an ontology. You may want to, like we said before with threat assessment, can we give a probabilistic inference on the likelihood that a certain ship is a threat, to another ship that we're protecting. But the reasoning is a big benefit to using ontologies, mainly because we can generate a lot of new facts from existing facts using the reasoning. So here's a simple example: searching a message ontology. So this taxonomy was developed based on analyzing the semantics of example tactical communication in a Navy piracy interdiction mission scenario. While this specific event is fictitious, the message types in this illustration exemplify the kind of messaging used during missions of this type. If we formally represented this Navy message taxonomy within our applications ontology, then use these terms to tag actual message data by type, a search for the term message would return all known commands, reports, and responses in the knowledge base. However, a search for commands would return only command subtypes, such as observation commands, movement commands, report location commands, and attack commands that were sent by the carrier bridge. Finally, a search for attack commands would return commands by the bridge to attack the bogies. In this way, the taxonomic relationships in an ontology help to structure the knowledge base into explicit type-subtype relationships that can be exploited in search, navigation, and other applications. And this is something we will be talking about in more detail in the next upcoming sections. So in conclusion, ontologies transform the meaning buried in inaccessible application code into accessible knowledge structures that can be exploited by many intelligent applications, from data navigation to advanced reasoning. Okay. My WebEx skills are, I have to learn how to stop sharing and then. Okay, so we have a few minutes for questions. If anybody wants to raise their hand and ask a question, you can feel free to do so at this point. You'll have to unmute yourself. You can unmute yourself if you want to ask a question.
So when you're working with the ontologies for reuse, is it just easier to reuse what someone else has created, or is everything we do unique? What makes it easily apply across the domains?
Well, let me give you two answers to that question. In comparison to data models, the idea is that we can more fully capture the information in our data such that it would be easier to reuse for other applications. Now, there's a second question about how easy is it to use ontologies? Do we have to always build them from scratch, or can we reuse those? And if you're following, proper ontology development practices, then it should be fairly easy to reuse ontologies. The biggest challenge to reusing ontologies typically is, not that you didn't create it, right? There's a tendency for people to want to always create their own, stuff. But there's a lot of efforts out there to create existing standard ontologies that, even if you don't use them, would already, give you a head start in developing one. Did that answer your question, Lee? Or?
Yes.
This is Carlos Alvarado. So, the question for you is, what is the biggest challenge you see for military applications?
With ontology development?
Correct.
I mean, one big, I don't know what the biggest challenge would be, but I know one challenge we face is, working with realistic data. So, a lot of the data is, sensitive, if not secret and classified. And that's always helpful when developing an ontology is, can you see the data? Can you understand how the data is going to be used by, downstream applications? Those are sort of things that are key to developing an ontology. You can still develop ontologies without that data, but there's always a gap between what you think the end user would need and what the end user needs. Carlos, do you see any areas where you find you think it might be challenging over and above other, domains?
Especially when you're building architectures and you're building cross-service architectures to be sure that the meaning of the data represents the same. Like, for example, when you're describing a tank, what the specifics of the tank says, it has different meanings for different services.
Right. A classic example is unmanned aerial systems. Different people call it different things, like remotely piloted vehicles, drones. There's a whole long list. So one of those things is, ontologies can be helpful is capturing those different ways of saying the same thing, or can be helpful for disambiguating, the meanings of, like, tank, whether you mean a water tank or you mean the vehicle, tank.
On that point though, when we take different groups data that they've modeled and try to reason across multiple groups, we saw it even in the stuff we did for the propulsion group. It gets difficult really fast because the originator of the model had something in mind that's different than another group, and you're ultimately then on the hook to try to get them to be pulled together and reason across them. I think that's been a big challenge, and that's why people tend to just recreate the wheel.
Yeah. If you're doing ontology correctly, there's no magic there. You have to learn what those different intended, meanings are. The upside of an ontology is once you discover that, you can then capture that in the ontology so that the next person who comes along doesn't have to relearn that lesson.